Welcome everyone. In today's tutorial we are going to be learning how to create this rainbow lightsaber radar effect. So essentially what we're going to be doing here is we're basically going to be spawning all these circles from the center of our canvas outwards in one direction. And that direction is just going to look something like this. We're just going to start these off all flat, going horizontally. But eventually, when we move the mouse, we're going to create that nice little fade effect. Around a lightsaber along the lines of that. And to do this, we are going to be using math, sine, and cosine functions. So I promise those sound confusing at first. And I remember when I was in trigonometry class, I never paid attention. And I kind of regret it a little bit, but it was so boring, I don't really blame myself. Now I have a reason to use it, and once you learn these sine and cosine functions, I promise you they are just so freaking easy to use. It's gonna become second nature when you do it enough, so let's get right on into it and learn how to use these functions to create what we see right here. So starting from a blank template, this is what we have. This is the canvas boilerplate. You get the deal. We're going to go through this and remove exactly what we don't need and keep exactly what we do need. So up top, we don't need to import any util stuff. I might even remove that from the boilerplate, just kind of redundant. Going downwards, this is all canvas setup stuff we need. We're going to be using our mouse coordinates at some point to move the lightsaber radar thing. Colors, we don't need this because we're going to be generating these automatically. We can keep all of these event listeners because we need to listen for mouse move and resize event. We have our object class. This is just a generic class, but we're going to be renaming this particle so we don't have something that's just generic. So let's just do that now. We can get rid of this comment, doesn't really matter. We have our implementation, same deal. We don't want to reference just objects, we want to reference particles. So on init, when our page loads, we're going to be assigning particles to an empty array. We're going to be using a for loop to populate this array, and this is basically going to create all those particles along that line initially, which we will eventually move following the mouse. Then we have our animation loop. And always want to keep the animation loop if you want stuff to move, otherwise it's just standstill, boring. So what we can do here is get rid of fill text. We don't want this stupid text running around. Just going to save this. It's going to refresh automatically because boilerplate's a boss. And this is kind of where we want to start off at. So only thing we really did was change our class name of object to particle, and that's a great start. So pretty much with all canvas pieces, the very first thing you want to do is just spawn your particles and then place them on your screen somewhere. You want to render them out on the screen before you add any movement. So that's going to be the very first thing we do. So looking at our particle class, we have a constructor, and this constructor is basically what determines your particle's individual properties. So our particle is going to have an x coordinate, a y coordinate, a radius, and a color. So these are things that are all going to be independent from one another as we create different particles. We have our draw function. All this does is draw a circle. This is basically what's responsible for how our particle looks. And all this code right here just says to draw as a circle, basically a particle. Then we have update. All this does is call this.draw. Technically, we don't even need update. We could just write all of our update code within draw. But to keep things a little cleaner and keep things segregated, basically I want to make sure that draw is responsible for how the particle looks, and update is responsible for how we're actually moving and manipulating the particles. So now that we have our particle in place, what we can do is we can go ahead and start creating particles on the screen. And to create multiple particles on the screen, well, we need a particles array, and that's what we just created earlier. This is basically what's going to contain all of our particles, which we render out at the same time. So if we were to just create one particle and render it out, assign it to a variable, well, we just have one particle. But when we store all these inside of an array, now we automatically have the ability to render all these particles out at the same time. So inside of this for loop, which says run 400 times as specified by this 400 right here, we could say our particles array, we want to push in a new particle for each iteration of this loop. So 400 times we're going to be pushing a new particle into our particles array. So our particle takes an x, a y, a radius, and a color. So the very first thing we're going to put in here for x is going to be canvas width divided by 2, which is going to put our particle right in the center of the screen. If we want this right at the center of our screen vertically, well, we will add canvas height divided by 2. Then we need to specify our radius for the circle particle, and I'm just going to go with 5. That's going to give us something smallish, I guess. You get the deal. And then color, I always go with blue. It's my go-to. So saving this, refreshing, nothing happens. How wonderful. Kind of expected, I guess. But if we go ahead and console log out particles after running this and refresh the page, you'll see our particle object being stored in here 400 times. And these are all different particles, meaning their properties can all be manipulated independent from one another. So we're doing great, we're on the right track, but now that we have this particle array, we now need to render each of these individual particles out on the screen. And to do this, we're going to focus inside of our animate loop. So boilerplate code, template code, I kind of hate the word boilerplate. That aside, template code right here, basically we're saying we want to go through each object within an object's array. So we want to change objects to particles and say for each object or each particle, within our particles array, we are going to call that particles update function. So we have our particles array, we're looping through it, and then we are calling this right here, update, for each particle in this array, which in return calls draw, which in return draws the particle on the screen. So if we save this and refresh, now we have 400 particles being drawn right in the very center, and you can see just how pixelated they are because you draw stuff on top of each other. It's just going to be really, really pixely like a 8-bit video game. Now that everything's being updated, the next thing we want to do to create that lightsaber effect is just get all these particles spread out from each other. And we're just going to draw them from the center, going to the right side of the screen. And to do this, we want to go back to our particles loop. So if we want to draw this from the center of the screen and start getting particles to shift to the right, well, what property do we have to edit? Our properties are right here. Can you tell me? No, this is a video. So the property we want to edit is going to be this dot x, or x coordinate. So what we can do is, focusing back in our for loop, and I'll make this a little bigger so it's easier to read, our x property is going to be this guy right here. And if you have trouble remembering which property goes where within this particle object creation, what you can do is within the loop, create a constant called x. And this is just going to be our x coordinate, and set it equal to what it was earlier, canvas width divided by 2. So now we know what variable, what kind of content is being stored directly within our x coordinate, which is canvas width divided by 2. So in order to get that effect of things going to the right, we need to add some sort of number onto this variable. So if I go ahead and add, let's say something like 100, you're going to see everything shifts to the right by 100 pixels. But that still doesn't solve our problem because everything is still pixelated on the screen. This number right here needs to be different for each iteration of this for loop. And if you think of how to do that, well, the best way is to select this I let, this I variable. So if we go ahead and replace 100 with I, well, for each iteration of this loop, we are only adding on I to our canvas's width divided by 2, so half of the screen. And I increases for each loop. So first iteration of the loop, we have 1. Second iteration of the loop, we have 2, third, 3, and so forth up until we hit 400. So eventually, we're adding on 400 pixels onto our canvas width divided by 2, and that's going to give the effect of each particle having a different x coordinate. So if I save it by adding on I, you're going to see our particles go all the way to the right-hand side of the screen. We have 400 particles right here to the point where we can't even see them. So let's go ahead and decrease 400 to something like 200 to start. Let's make sure that these are all visible, and now they are. So this whole line consists of 200 particles, but now these are 200 particles individually that we can move to start creating that radar lightsaber effect. So to clean this up a little more, let's go ahead and create a constant for y, and then we'll take our y code right here and make sure that this is being assigned to y. And then we want to make sure that we are replacing this with our y coordinate. And this is just a little easier to read because now we know our y is equal to canvas height divided by 2, and that our particle instantiation starts off with an x and y coordinate. It's just going to do the exact same thing, just a little easier to read. So the next thing we need to do is start moving this line around a circle basically to create windshield wiper, lightsaber, whatever you want to call it effect. And to do this, this is where the Math.sin and Math.cosine functions come into play. So to get this effect, what we want to focus on is this I value right here. I is basically the distance from the center for each individual particle. And when we start multiplying I by Math.cosine, well, the position of this line, the position of each individual particle is going to start shifting around the outline of a circle. So looking at the whiteboard right here, let's say for instance that we have 3 particles. So 1, 2, 3. And these particles are basically representative of that line we have on our canvas piece. The only difference being is that they're spaced out so we can really see what is going on here. So 3 particles. Let's focus on 2 particles. This is just the center of our canvas, which we can notify by red. So red is going to be center. Purple, red plus blue, whatever you want to call it. So this is the center. These are our 2 particles. What we need to do to these particles is start moving them along a ring. So do my best to draw a circle here. My beautiful drawing skills. Another circle right here. We need to get both of these particles moving to different locations along this ring. So this guy right here needs to start moving upwards, and at the same time, this guy right here needs to move upwards so that these connect a line. So how do we get these particles moving upwards to these locations? The answer is through math, sine, and cosine. This guy right here, this particle, if we take its x and y coordinates, and to make this as specific as possible, let's go ahead and make these actual coordinates. If we go ahead and take its x and y coordinates, which are going to be equal to 1, 0, and then we go ahead and take our x coordinate, 1, multiply it by math, cosine, and then the angle we want to move the particle by. So this angle right here is what we want to put inside of math cosine. And this is always going to be in radians. Radians is just a fancier version of degrees. So while this would be something like 50, 57 degrees, it would actually be about 1 radian. So if we go ahead and multiply 1 by math cosine 1, this is going to produce any value from -1 to 1 right here. If we multiply it by that, well, our x-coordinate is going to be something like, let's just say, 0.5 as a result. So our cosine value is going to be 0.5. And if we do the same exact thing for our y value, 0, but multiply it by Math.sin, and then whatever angle it is at, which is also going to be 1. So still multiplying it by this angle right here. If we go ahead and multiply it by that, well, our y value is going to shift upwards. So instead of being 0, we're actually going to get something like 0.6. And then our final value would be 0.5, 0.6, which is this exact value right here on the unit circle. So essentially, in order to get the coordinates for this one point right here, we need to do this equation, multiplying the x and y coordinates by math sine and math cosine. And just to be extra clear, this is the y, this is the x. X always goes with cosine, while y always goes with sine. And same deal for this little guy right here. If we want to move this along the same path, just farther along the x-axis, well, this is probably equal to 2, 0 instead of 1, 0. But you'd still do the exact same equation. You'd still multiply 2 by math cosine 1, and you'd still multiply y by math sine 1. These are just angles and radians. And when you do that, you get this location right here. It's just a little farther up because the initial value is bigger. So that's how we're going to get the effect of moving these along some sort of ring, is by using sine and cosine. So before we actually get to animating this, the first thing we'll want to do is just play around within our init function on refresh to make sure that we're moving this around the screen. So I is basically our offset. This is like the power value of how far from the center should each particle be distance-wise. So we're going to go ahead and add I onto y as well. And when we do that, we are continuously increasing our y coordinate, which is why it starts going downwards diagonally. So we're both increasing x and y. And as mentioned, as we start multiplying this right here by math cosine, because this is our x-coordinate, by some sort of radian inside of this, well, our x values are going to change. So if we go ahead and do 1, you'll see that they start shifting downwards, and then we'll do the same thing for our y. We'll add in math sine 1, and now we have something that's pretty similar to what we saw on the actual whiteboard drawing. The difference is our angle is going downwards instead of upwards, because if you think about it, Canvas's coordinate system is actually reversed. Our y values start from 0 and go downwards instead of upwards like it normally would within a unit circle. So if you want to replicate what we have on the whiteboard, you just set sine 1 to sine -1, and then it's going to go upwards in the other direction because we're basically just reversing the direction of our angle. So if we want to go ahead and start moving this counterclockwise, what we can do is change our cosine to a bigger number, because as we go along our unit circle, this radians number is going to increase. So if we go ahead and add 2, well, now we are going further along that axis. If we add 3, we just keep going, and then eventually when we hit math pi, we should get the full distance in which our x coordinate can go to. And if we do the same thing for Math.sin by replacing 1 with math pi, well, now we are on the farthest edge of the left-hand side of the circle. So if we start editing this radians value over time to follow our mouse, well, this is what's going to create the effect of all the particles just following it over time. So what we really need to do is edit each of our particles' x and y coordinate within update. For every refresh of our animation loop, we're going to be editing these x and y properties based off of the angle of our mouse from the center of our screen. The angle that we produce here is just going to produce that animation effect for the circle. So what we can do is we can go ahead and keep our init code for now just for reference. We're going to be editing this a little later on, but inside of update, we're going to want to say that our x coordinate for each individual particle is going to be equal to basically this right here. The only difference is going to be is instead of math.pi, we're going to be using a dynamic variable produced from the location of our mouse. To make this code a little easier to read, we can do a few things though. One of the most common things I do is instead of canvas width divided by 2, I go ahead and replace this with a object called center, which has a property of x, and that just lets me know I'm at the center of my canvas. But if I want to do this, I have to go ahead and actually make the object. So at the very top, I'll just create a object called center and then give it an x coordinate of canvas width divided by 2. Simple enough. And then y will be canvas height divided by 2. So now I have one constant that always tells me the center of my canvas. And then I can do the same exact thing for my y coordinate. Instead of referencing canvas height divided by 2, I can now just reference center.y. So if I save this, you'll see we have some errors over here, and this is because I is not defined. I is only going to be available within this for loop. It's not available within our individual particles update functions. So what we need to do is add a new property for each particle, and this is just going to be called distance from center, because that technically is what I is the particle's distance from the center of the screen. And this is going to be equal to, which we will pass through as a constructor argument. So take this, put it right there, and now whenever we are creating a new particle, what we can do is assign a distance from center property to each individual particle. And remember, distance from center is just I. So all we have to do is put I as our 5th argument here. And then since we don't have I available to us within update, all we have to do is reference this dot distance from center, place I here, and now we know exactly what is going on. So we get the same effect as before, but now this is happening within our update function, something being called over and over again, not just on init. And looking at this, I almost forgot cosine for y should be sine. Make sure you do that or else you won't get the correct values. And that is actually going back to where we were earlier. So next thing we need to do is make sure that this value right here is not math pi, but some sort of angle, some sort of radians value that changes over time based on our mouse's position. So instead of math.pi, what we're going to do is add in an angle let. And to create this angle let, we'll go to the top where our global objects are and say angle is equal to 0. This is where the starting angle of our line is going to be. So if we set this equal to 0, everything is equal to 0, so it just goes straight to the right. It's so cool. It's so cool. Kill me. And now that we have this angle property, which can affect the math sine and cosine values of each individual particle, we need to get the angle of the right triangle created from the center of our screen to wherever our mouse is. So what do I actually mean by this? So let's say this right here is the center of our canvas, and I'm going to use red for our actual pointer. So our pointer looks something like this. Well, how do we get the angle of this right here? How do we get this angle? If we start moving our pointer upwards in this direction, well, this angle is going to increase. This is the guy we need to get. And to get this, we need to know the x and y distance from here to here. We're going to use these two properties in an a tan 2 function. And when we use this, y goes here, x goes here, it automatically produces the angle of this right triangle in radians. So this returns radians. So beautiful. And this radians value is exactly what we're going to plop inside of our sine and cosine functions. So right now, looking at mouse x and y, let's go ahead and console log out mouse to see exactly what we're getting on the screen when we move our mouse around. So these are all the coordinates, and you'll see as I move my mouse to the top left hand side of the screen, we're getting closer and closer to 0. Although that's not really what should be happening here. Our 0 coordinate is right here in the center, so we need to make sure that we translate our canvas to start from the center whenever we're moving our mouse around. And to do this, we have our client X and client Y, which are these guys, and our console down there. All we need to do is subtract our canvas width divided by 2 for X, and then our canvas height divided by 2 for Y. And when we do this, we basically translate our mouse coordinates to start from the center of the screen instead of the top left. So if I start moving to the top right over here, you'll see our Y value is negative, our X value is positive. Y is negative because remember our canvas coordinates, Y is reversed. If I start going downwards, then everything is going to be positive. And we basically have like this quadrant in which things go positive and negative between each other. So this is exactly what we want to start producing that angle result from the right triangle of our mouse. So the next thing we need to do is set our angle let right here. So angle is going to be equal to math.atan2, which is going to return a value in radians. And the first argument here is going to be a y value. All we have to do here is input our mouse y and then input our mouse x. And let's go ahead and see what our angle produces. So now you'll see we are getting radian values, which start off really small. We keep going, it just keeps increasing, and it's going to keep going up until we hit math pi, which is going to be 3.14. I remember, me good at math. And then once we hit side, 3.14 just about, and then we go into the negative values, which is basically like the same thing, but for the top quadrant. So we're getting exactly the angle produced by wherever our mouse is on the screen. And now that we have this angle, what we can do is use it directly within our update function. It's already there. I just noticed that that was actually working without me even realizing it. So cool. Since angle is global, we can just use it directly within this update function, even though it might not be the best code practice. I don't really care because it works at the moment. And this initial effect is exactly what you need to start creating canvas games for a lot of stuff, because you need to angle things such as your cannon, your projectiles. You need to angle them from point A to point B to determine things like where your projectiles go, where your laser beams, your cannon shots, whatever it is. You're going to be using this a lot, which is why I'm doing this episode right now, is to prepare you for canvas games. So honestly, this is like the most trash lightsaber I've ever seen in my life. So let's go ahead and make this legit, like the most legit Mace Windu, TikTok worthy lightsaber you've ever seen. You know, it's like, it isn't even really a lightsaber. It's whatever you want to call it. And that's kind of like just how canvas stuff goes. So to start making the same effect we have right here, we need to do a few things. The most notable is change the background color of our canvas. And you've probably seen me do this so many times. To do this, we just need to focus on our animate loop. Change clear rect to fill rect, which is going to give us this beautiful blue background. I love it. And then we don't want blue. We want to change this blue to RGBA, which takes RGB values 0 to 255, 0, 0, 0, 1.1. This is the alpha value. The last one takes any value 0 to 1, and it determines how quickly the background is refilled. So if we give it a value of 0.1, that means we have a transparent refill background, which is going to give us that fade effect that you see whenever we move this around. So looking pretty cool. Let's go ahead and change the colors of each individual particle starting from the center. So this is going to happen inside of our init function. Instead of blue, we are going to use HSL, which stands for hue, saturation, lightness. Hue takes any value 0 through 360. We're going to start with 0. Saturation takes any value 0 to 100%. Start with 50%. And then lightness takes any value 0 to 50% as well. So cool. And we save this and we have a nice red shade instead of blue. Welcome to the dark side. So what we want to do here is change this hue value over time for each iteration of our loop. We want to make sure we're getting all the values starting from 0 to 360 spaced evenly. So we want to make sure that we're replacing 0 with a hue value instead, and this hue value is going to be something that we can increment within our code. But we can't just put hue here inside of a string, or else the string isn't going to render our code correctly. So what we want to do is replace our quotations with backticks instead, and when we do this, we can use a template literal, which is a $sign opening curly bracket, closing curly bracket around whatever you want computed. And now you'll see this lights up as white. This means we can use something like X or Y for this value right here. But we don't want to use X or Y. We want to use a value called hue. And if we set this to something like 30 to start, we're going to get a hue value of 30. You'll see it rendered out on the screen. But hue can't just be 30. It has to be something that changes over time. So we want to get an even value that when multiplied by 200 equals 360, because we're just going to be adding this value onto itself over time. And that's going to produce that nice rainbow lightsaber that we want. So outside of our for loop, what we're going to do is create a constant called hue increment. This is what we're going to increment hue by over time. And this is going to be equal to, and actually let me make sure I'm writing this code correctly, hue increment is equal to 360 divided by 200. So 360 is the max value that we can put in for our HSL, for our hue right here, and 200 is the amount of particles we're actually inputting onto our screen. So to make this code a little cleaner, what we want to do is create another constant called particle count. How many particles do we actually want rendered on the screen? We're just going to set it to 200 right here. And now we can replace our 200 values where we're referencing our particle count right here and right here. And now if we ever want to change our particle count and keep our color gradient in place, we only have to do it in one spot. We don't have to do it in two. And we remember exactly what 200 actually stands for. It stands for particle count. So if we save this and then console log out hue increment, let's see what we get. We get 1.8. So now if we take 1.8 and multiply by 200, we get 360. So now we can get an even amount of values for our hue and make sure we get that nice rainbow gradient effect. So now inside of our for loop, now that we have 1.8, we want to make sure that we're referencing 1.8 right here where hue is. So instead of using hue, we're going to input hue increment. We can get rid of this hue constant. So now everything is just going to be equal to 1.8. But when we start increasing this over time by multiplying it by I, watch what happens. We're going to get this nice rainbow gradient. And to really see how this works, we can go ahead and console log out this computed statement right here, hue increment times I. And you'll see, since we're multiplying 1.8 by I over time, which is 200, we're just getting a different iteration of our loop each time. Well, eventually we're going to get all these even values in between 360, which gives us all of the colors of the rainbow. So cool. That's how you do it. That's how you do it right there. Increment those hue values. So this is looking pretty close to what we have. You could say, oh yeah, I want to keep it as is, but no, that's not everything I did. You'll see right here, as I start moving my mouse around, this is actually a really smooth movement. It actually has a little bit of easing involved with it, which means it slows down or decelerates or accelerates over time. And right here, it just follows my mouse directly. If that's what you want, that's cool. Fight off people with your instant lightsaber. But if you want this slow lightsaber that like gives you a little bit of delay so you can die easier in Star Wars, then this is what you want. So in order to get this ease, what you want to do is actually use a animation library. And when you use an animation library to set your mouse's X and Y coordinates within mouse move, well, you can add on those easing effects really easily. So the animation library we're going to use is called GSAP, stands for Green Sock Animation Platform. Have no idea what green sock means, but you know, that's just what they chose. We want to go ahead and use our terminal. If you're new to terminal, go ahead and bear with me for a little bit, but this is the correct way to import libraries in your project because it makes things very explicit. What's in your project, what's not. We are going to cd, change our directory into our project. And you'll see if I go inside my Finder, I pretty much store all my Canvas projects inside this Canvas directory. And this is going to be called, what did I call it? Rainbow Lightsaber. So what I can do here is type cd into my terminal and then drag this onto my terminal, and I'm going to change my directory in terminal to this directory right here, Rainbow Lightsaber. If I ls, which means list the contents of this directory, I have everything that's going on over here. So this is just a one-to-one representation of what's happening in Finder. It's just that we're doing this in terminal so we can run a few terminal commands to install Greenstock Animation Platform, GSAP. So to install GSAP, when you're inside Rainbow Lightsaber, you want to run npm install gsap-save. npm is a package manager that comes with Node.js by default. So if you try running npm install gsap and this just doesn't work for you at all, you need to make sure that you install Node.js. So just type in Node.js, go to their website, and then download whatever is the latest version for your computer. Go through the installation process, and then once you're done, you should have npm installed and you can run this command. You can also go ahead and run yarn if that's another package manager you want to check out. That's typically what I use. It's a little faster and cleaner, so I typically go with that, but npm works just as well if you want to do the simplest install possible. So once you run that command and you go back to your project, you're going to notice inside of a package.json file that you now have a dependency called GSAP. So now we know our project makes use of GSAP because of this package.json file, and we know exactly what version of GSAP that we have, which is 3.5, because if we were using a previous version at some point in time, well, the APIs, the functions, the library might be different in some way, and we might not know what we're doing. So this is super helpful as a developer to know what libraries your project uses and what version they use as well. So once this is imported as a dependency in package.json, you can go to the top of your file and type import GSAP from GSAP. So this is the library name, and this is basically the API. This is going to contain all the functions similar to C right here for Canvas. This will contain all the functions we need to utilize GSAP's library. So if you ever need to use GSAP in some way, you can go to their website and find their documentation on what to use and how to use this. But I'm going to spare you the pain of actually looking through docs because no one likes doing that, unless you're really frustrated with your project at least. And we're just going to use GSAP directly. So in order to use GSAP, we can now use this GSAP object that we imported and say GSAP2 mouse, comma, and then create an empty object. And inside of this empty object, we're going to have an X value and a Y value. We're going to set X to this right here. And then we're going to set Y to this right here. Now that we do this, we can delete this. And now GSAP is going to run this code. What does this actually mean? So GSAP is automatically going to apply easing, acceleration, deceleration when we set our X and Y coordinates to this value. So basically we're saying we want to reference our mouse object right here and then create some sort of interpolation for our X and Y values over time. So we're not just setting X and Y immediately, we're actually interpolating to them, meaning we're increasing or decreasing the value over time. And the default time in which you increase is going to be 1 second. You don't need this duration property right here, but by default, when you use 2 with GSAP, duration is going to be set to equal to 1, and it's going to have a default ease associated with it as well. So this is really all we need to do. And we hit save, you'll see we now have that really smooth effect of all of our objects actually following our mouse, because instead of setting X and Y to this immediately, we are now interpolating those values over time. So now we get the really cool effect of the Rainbow Lightsaber radar, and that is how it's done. So, like always, it's time to really fuck around with this thing and just see what kind of crazy stuff we can do. So this is effect, end of tutorial, we're done, but not really. How do we make this even crazier? Well, let's go ahead and speedrun it. Our opacity is going to be 0.5 for extra lightsaber rainbow, color wheel rainbow ball. I'm going to affect my radius over time because just 5 is just too boring for me, you know? So what I'm going to do is create a radius increment and set this equal to, what is my max radius going to be? I don't know. Let's say 30 divided by particle count. This is going to be what my radius increases by for each particle. If I put radius increment inside of here and multiply it by I so it actually increments over time, nothing happens because I suck. And now I need to think real hard of what's going on here. All right, so the issue is I'm on like the one I showed you guys earlier instead of the one that I'm developing now. I feel bad Get out of here. So let's go back to the new one. All right, this is this is the one we meant to be editing. So now I just created like a baseball bat, ice cream cone, snow cone. This is like a baseball bat lightsaber. This is what you really want when you're in Star Wars. I like it. I kind of want to reverse this. I want to make sure like the outside is small and the inside is big. So instead of just incrementing my radius over time, I'm actually going to decrement it, I believe the word is. And I'm going to take our particle count and then subtract this value. So that should give us big in the middle, small on the outside. I don't know if that's really the right way to do it. I'm pretty sure it is. Okay, it's definitely not. My bad. It's not particle count. It's actually the main radius that we want to subtract from. So our main radius is going to be equal to 30. And since I'm using 30 in 2 spots, I'm going to make a constant called radius, base radius, and set this equal to 30. Replace 30 everywhere with that. And now I have like a little party hat cone instead. It's my favorite. So now I can basically edit this in one spot and it should affect our code correctly. Pretty cool effect, honestly. I dig it. It's like we're starting to get into the realm of 3D here. Woo! That looks like something I should not be showing on a kid-friendly channel. So I'm going to get that off and we're going to go back to party hat mode. Next up, if I want to increase the length, which I kind of do, I'm going to increase our particle count, give us a big party hat, and we're going to get really crazy with this now. Now we're going to start moving the particles in different directions over time. So if I go ahead and start multiplying this by Math.sin for our y, and then Math.cosine for our x, Math.cosine, nothing's going to happen just yet. It's just going to break actually. What we want to do is add a radians value that increases over time inside of here. So what we can do is within our animation loop, we'll create something called timer, set it equal to 0, and this timer is going to increase by 0.001 over time. And now we can begin using this timer within particle update. So if we pass this through as an argument for each individual particle, now we can make use of it within our update function right here. And now timer is going to increase inside of this update loop. So I save this and refresh the page. Well, now when I move my mouse, we get a completely different look of moving this around. It's kind of like we're in another dimension or looking at this from a different perspective. So over time, this is going to expand our particles all the way to the right hand of the screen. Eventually, they're going to go back. And just looking at this is already starting to get pretty messy. One thing we can do is we're going to create a constant and take out the sine and cosine functions from math directly by using this destructure operator right here. And now we can get rid of math dot all over the place. Save this, just a little cleaner. We can even do the same thing for this dot distance from center because that's kind of long. We can just go ahead and destructure distance from center. Say it's equal to this. We're basically just popping this off of this. And now we can remove this. We can remove this right here, and we can remove this right here. Saying this so much, and this still works exactly the same, so a lot cleaner than what we had previously. And one more thing you can do is distance from center is just so long. Just make this a little more compact by saying dist from center instead. And make sure you place it up here in the argument so that we're assigning it correctly. And now we have more understandable code, something that like I can read better instead of me just wondering what the heck I'm doing. So now what I want to do is add on dist from center here within our cosine function. It's going to make sure that our sine and cosine values are different for each individual particle. And now, oh no, I did not mean for this to happen. You know, sometimes you just edit the code and this crazy stuff happens. And this is one example of that. I don't even know what to call this. It's like a mouth, I guess. This is like a big talking mouth. Let's see what else we're going to do this. Oh god, if this is just supposed to be a lightsaber tutorial. Let's keep going. I just want to see what this looks like with a base radius. That's different. It's just freaking crazy right now. I think like my mouse is a little off because angle right here isn't negative or something like that. I feel like that feels more natural for some reason. I don't know why. So I'm just going to go with that. Let's just make our radius the base radius. Save that. Oh no, what did I do? Base radius 30. I want it to be 3. Okay. I feel like we're coming back to normal now. This is a pretty cool effect, but not cool enough. I'm not done. No way. So now if I do the same thing by multiplying on y, timer, dist from center, get a completely different effect. And this is kind of like a little hourglass, which I'm digging. It's kind of like a 3D galaxy that we're getting into. Let's do the same thing for y. Just go ahead and multiply this by cosine distance from center. Now we just get boop, 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 boop. If I make the sine, though, we get something different. Ooh, not even close to as interesting as before. Let's keep it as cosine. And just keep timer in there. Just go crazy with this. Yeah, alright. I think I've had enough fun, honestly. This is where I'm going to call it at. It's just this hourglass figurine. Probably had some cooler stuff earlier, but, you know, looks cool to me. So I hope you guys enjoyed, learned a lot, especially about atan 2, how to get an angle based on the mouse positioning, and using sine and cosine, because those are the most important lessons to take away from this. So soon enough, what we're going to be doing is taking everything we learned here and a little bit of some of the previous episodes and using it to create a canvas game. I know a lot of you have been asking for that, and believe me, I'm listening. It's just in order to get this in a concise format, or as concise as possible, while keeping the understanding there, need to make sure we know exactly what we're doing. So we're going to be using a lot of this, and I hope to see you there. If you would like to learn more Canvas tutorials, more about web app development, how to create your own website or web app, head on over to chriscourses.com. I have a number of free and premium courses to get you started with web development. I can't recommend this one right here enough, the Web Apps for Beginner course. Basically just has so much content packed into one full course on how to create your own app, in which you can register for accounts, you can reset your password, create all this functionality that you need for people to log into stuff and post on things such as your forum. So be sure to check it out. Let me know if you have any questions in the comments. Subscribe. I'll see you in the next episode. Peace.